This is our last set of notes from my seniors. After this, it will be, no, I said seniors. Are you a senior? We covered 3 sets of monomaterials yesterday: liquid crystals, the other 2 polymers, and what's the first one? What was it? Yeah, biomaterial, those 3. Today we're going to cover the last 3. The first of them is called nanomaterials, okay? Nanomaterials are defined as substances that are made that are between 1 and 100 nanometers scale. About 3 years ago, I had a workshop that I went to, which I was all excited about. It was about the study of nanotechnology and the application thereof. And I'm going, oh, great, I'll be able to do all these nice. And the professor sat there and talked at us for 3 hours about how you do this thing in theory. In other words, there were no labs, there were no processes. He just made little pictures of it, okay? Because the scale is so small, we're dealing with atomic, atom-based structures, okay? Now, when it comes to nanotechnology, nanomaterial, there are 2 main uses that we come up with. The first one is cellular repair or at the cellular or DNA level. So using structures to repair basically at the DNA level, atom upon atom kind of structural repair. Okay? The second use is electrosensors or microchips. Okay? The main purpose of his workshop was talking about how they're actually making microprocessors that are atom size. So they're small enough that you can be literally adding atom on top of an atom to make a microchip. That's nanotechnology, right? Now, there are 2 main problems with nanotechnology. Okay, the first one is controlling the processor, okay? Because they're so small, when you run a computer, what is the main problem with running a computer? Does anyone know? Something has going on today. What would you say? Yeah, heat. Computers get hot. And if you do it at an atomic level, would that cause those atoms to break down and separate apart? Any kind of heat. It's just so small. So we're now up to about, I believe, minus 50 degrees Celsius. When they first started this, they were like minus 200 degrees Celsius to keep the processors from overheating, okay? We hope at some point in the future be able to room it up to room temperature. But these are like the super processors that work through. Does that make sense? The second is the controlling the flow of data. What do we mean here? We're meaning to have a matter of privacy. Privacy, P-R-I-V-A-C-Y.
Don't ask me. I'll try.
Okay, I'm not, that's why God made spell checkers. All right, let me explain. What a lot of times corporations will do is they'll put a nano chip into like the t-shirt that you just bought. Okay, like in the label, in what looks like ink, they'll put a little microchip, a nano chip. Well, the main reason is for inventory. They don't have to sit there and count every t-shirt in a box. If they have a nano chip inside, they only got to pass over the box and everyone will activate. Now, what's supposed to happen is after that, they're supposed to turn the chip off, right? But do they always turn the chip off? No. And let's say you buy your t-shirt with a credit card or a debit card or any other kind of card. Is that t-shirt now attached and fixed to you? Yes. Now, when you walk in and out of Walmart, you know those little sensors that are inside of there that go off if, like I have a couple cards that I put the wrong cards together. It sets the alarm off, going in and going out. Same kind of thing. If they have those sensors on, they can literally track you every time you come into the store, come in and out of the store. So privacy can literally become an issue because you're being tracked and you don't even know Does that make sense? Any questions? All right, so that's the first one, nanotechnology. I can't go into structure because we're literally talking atom structure formation, and it's very, very difficult to work through. All right. So second material we're looking at is called thin film material. Thin film materials are defined as coverings of material of thicknesses between 0.1 to 300 micrometers. That little funny looking U thing is micro. Means 10 to the 6th. 0.1, 10 to the 6th, or 300 times the 6th. It's actually 10 to the minus 4. Right? A million. Oh, a million. Oh. Okay? Gotta remember to slow down because you need to write this stuff down. We all good? Okay. Now the main uses of thin film. Okay. Microelectronics. Back when I was your age, and we wanted a radio in the car or any other device, what did you have to have? A nice little antenna waving out, a little bar antenna. Do you see many cars with antennas anymore? Well, some of them have a little small thing on top of the roof, but some of them, many of them actually have, if you look at your glass where it looks like it's tinted, you'll see little wires in there. That's your antenna. Literally, the antenna is built into the glass, and they put a thin film over top of it to apply the electronics to the glass to make it less seen. Does that make sense? Second is optical coating. So like protection on top of your glasses, also applying polarizing lenses. Things along those lines are all applied by thin film in order to keep it from being a problem. And the last type is metal cover, like Teflon. Okay, we want to apply Teflon to a pan, we use a thin film process. Okay. All right, all good? Awesome. All righty, now, the first type of way that we can do thin film process is called vacuum deposition. What we do in vacuum deposition is we take the object that we want to coat, right? We then take the chemical that we're going to use as a thin film. We then use a vacuum to suck, and we move the object, rotate it around to make sure it's evenly coated, and literally just pull the object over top of it, okay? And it's covering a substance with a thin film using a vacuum hole. So that's a definition of vacuum deposition. Okay. Covering a substance with a thin film using a vacuum hole. Now, the only major problem with vacuum deposition, because there's no actual bonding going on, it's just applied by a chemical adhesive, and those can come off if it's extremely heated up along those lines. Okay. The second type of thin film process, if you're still writing, so we get a few more minutes here. Okay. Second type is called sputter. Okay. So in sputtering, again, we take the object that was decoded, and we're going to electrify it. Now, when we electrify it, it's become what charge? Positive or negative? Negative. Electrons are negative. So electrify it becomes negative in charge. We then take chemical film material, but the film material has to be metallic in nature because it's positively charged. Okay, you should put that in there. It has to be a metal-based structure. Okay. Then, just using the opposite charge polarity process, it'll pull it across onto the material and cause it to coat evenly. Yes, ma'am.
Is that kind of similar to the lab we did?
What's that?
Was that kind of similar to the lab we did?
It's a little bit different. That's electrolysis. This is to make it a lot thinner. Yours was a lot thicker than now. You're talking, micros. Because the fact that that would be electrolysis and it's in a chemical solution, this passes on top of it. Does that make sense? It's similar, but it's not quite the same. All right? Are we good? All right, last type. I got to put a definition. Cover substance with a thin metal film using an opposite charge. Covering substance with a thin metal film using an opposite charge. And to be honest, they use this a lot in like scan electron microscopes when they're looking at bugs. So they get more detail, they'll cover the bug in a metal coating so they can, and of course, whoa, that's bad for the bug. Well, anything you put on an electron microscope, electrons are going to kill the bug. So you see those images the bugs are moving around? Not for long, because electron microscope will really kill you. So it's a bug. Oh well, there are millions of them. Are we good here? Any questions? All right, the last type is called chemical vapor deposition. Okay, chemical vapor deposition. In chemical vapor deposition, what we have, the surface is coated with a volatile stable compound at a temperature below its melting point. It is then reacted with a secondary compound which forms a stable adherent coating. Now, I'm going to give you quite a bit of time to write that down. That's the reason why I had it all down there. That's the full definition of chemical vapor deposition. Surface is coated with a volatile substance. That means it can boil, but we added a temperature below its melting point. Then it reacts with a secondary compound that forms a stable adherent coating. Now, when we do this, we're almost all finished here. When we do this, an example of a reaction is titanium tetrabromide plus hydrogen to form titanium plus 4 hydrogen bromide gas molecules. Why would I care for the formation of titanium onto a substance? Well, titanium onto a substance is beginning of the process to form Teflon. So this chemical vapor deposition is how we apply a Teflon coating to nonstick cookware. Does that make sense? All right. I won't make you use that equation until I promise. Just understand that that's a process that apply a metal in a chemical process and make it. All right, so we got 2 down. We did nanotechnology. We did thin film. The last and final are called ceramics. Ceramics. Now, ceramics are defined as inorganic solids that are normally hard, brittle, and stable at high temperature. Again, what does organic mean? Talked about it yesterday. Carbon-based. So inorganic, no carbon. So structures that in general do not have carbon-based inside of them. Okay? If I had a classification, I would be considered inorganic chemist. I prefer inorganic chemistry to organic chemistry. Okay. You all good? Awesome, awesome. All right, now, Base materials that form the ceramic compounds. I'm going to give you a list of them. You don't have to write them down. Okay, just so you know, there are more structures. Aluminum, alumina, which is Al2O3. Silicon carbide, SiC. Silicon nitride, Si3N4. Zirconium, ZrO2. Beryllia, BeO. Mild steel, and aluminum itself. A lot of these are like clays. And when I was in college, I had to take an art class. So I took ceramics. But after having my experience with bowling and knowing that I was a worse of an art person than I was at being a bowler, I took the class, pass, fail. So I got a B in the class. I passed. I was happy. Now, in terms of ceramics, there are two properties that make them incredibly invaluable. There are two properties of ceramics that make them invaluable. The first, they are incredibly strong. Ceramics don't break very easily, or when they do break, they'll shatter on a clean cleavage point. They won't brittle and fall into 1,000 pieces. Okay. Second, they have ionic conductivity. What do we mean by ionic conductivity? They allow for the transmission of, we talked about before in this class, electricity. So you can pass an electric current through ceramic material, certain of them based on which of the base materials you use. Now, in order to form them, there are two processes we're going to use, okay? Either intense heat or sol gel. Okay, either intense heat or sol gel process. Now the intense heat is the more common. It's the older process. It's the one that I used when I was in ceramics. Okay. Anybody ever done any ceramics in arts class? Alex, how did you get your ceramics to form up? You took the ceramic pot that you threw or made or coiled or whatever, and you put it inside of something. What did you put inside? A kiln. Very good. Now, did your art teacher tell you to be very careful about the size of the base when you put it in the kiln? See, when you throw clay, it's an incredibly therapeutic thing because you sit there and you beat the snot out of it for it, right? You pick it up and you throw it. You pick it up and you throw it. Does anyone know why you throw the clay so much? Right, to remove any air bubbles. Now, if you have a very, very thick base and you didn't remove any of the, as much of the air as you should, what will happen inside of the kiln as you heat it up? Yeah, boom, explosion everywhere. So it's very important to make sure that the base is thin and free of bubbles. When I was in ceramics class, we were doing what was called a raku fire. Does anyone know what a raku fire is? You take the pot while it's still hot in the kiln, pull it out, put it in like a bunch of leaves or paper or something like that with its blaze on, and you cover the garbage can. And it makes this really, really cool metallic kind of look to it. Well, as we were working, there was this really cute girl. And as she was moving the tines, they began to fall over. So being this chivalrous kind of guy who's maybe thinking about maybe try to ask her out for a date, I reached over and grabbed the tongs and helped her back up. Alex, what's the temperature of the kiln? Over 1,000 degrees. Metal tongs. What is going to be the temperature of those metal tongs as they touch the kiln? At least a couple hundred degrees. And that's why you have the nice little like asbestos gloves on. But being a chivalrous guy, I just grabbed it with my hands, right? Ah! But I did help her to keep it from them. I got myself a nice burn on both my hands. And she said, oh, thank you so much. Me and my boyfriend will be glad to take you out for dinner later today. Okay, you say all that burn for nothing. So a kiln is the first way we form. The intense heat sets the bonds, makes the ceramics. Are we good? All right, the second is a more common chemical process, okay? It's called sol gel. In sol gel, a chemical process results in the ceramic formation, okay? chemical process results in the ceramic formation. Now, one of the reasons we use sol gels is because we want really small chip particles that are uniform in size. These particles are called metal alkoxides. I can't quite pronounce it right now. Metal alkoxides. Metal alkoxides are defined as metal structures combined with an organic structure through an oxygen atom. Okay? They're a metal structure, any metal, aluminum, titanium, silicon, metalloid nature, combined with an organic structure, a methyl group CH3, carboxyl group C double bond O, anything along those lines, through an additional atom attaching the structure. Now, when we form that, we're going to usually generate a structure along the, like that. That's called an epoxide. Oxygen bonded to two different molecules, also referred to like an ether. Okay, but because there's metal in it, we call that ether. That forms a structure that allows for the movement of electrons across it. Okay, now that's one example of a possible sol gel formation. Okay. Are we good? Any questions? All right, now, a couple of the different uses of these sol gel ceramics are superconductors. Okay? Superconductors are defined as material with an incredibly almost frictionless conductivity. Metals with incredible, almost frictionless conductivity. So in other words, as electricity flows over top of it, they move so quickly that they don't generate much heat. And they generate very, very low friction. Okay. Yes, sir. It can be part, as the electrons go across it, they can generate a friction as the electron itself slides across it. And also the other material that we come back and put across it, which we'll talk about later in a couple of uses. All right? All right, now, a couple of the uses we have here. Uses for these superconductors. First of all, superprocessors. Okay, we use some of these ceramics. Remember we talked about the nano being a use of a superprocessor, but heat being an issue because the atomic level. These are larger. We can get these to almost room temperature. That's why a lot of computers, back when I first started teaching here, all the computer labs had to be air conditioned. Because if it got over about 50 or 60 degrees, and about 60 or 70 degrees, the computers began to break down and have to go wonky. But these supercomputers, we can get about room temperature, a little bit cooler than room temperature, and now to make them work more sufficiently and allow the information to fly over them without causing much heat. Does that make sense? Second are called magnetic levitation or maglev. Does anyone know what the main use of maglev is? We don't have many in the United States. Yeah, what they're referred to, Alex, as. You put in a gun, aim it. Bullet trains, yeah. One of the uses of this are bullet trains. Any of you ever been to Disney World? You went to, is that Universal Studios or Magic, whatever it is inside of there now? They have a roller coaster called the Rock and Roller Coaster. Do you know how the Rock and Roller Coaster works? Maglev, okay? Inside of the coaster are little magnetic superconductors. And the track itself has the opposite polarity. So inside of here, let's say these are all negatives, right? On each end, we put a positive behind it and a negative, or sorry, we ran positive in front of it and negatives behind it. What will happen is we put positive charges in front of it and negatives behind it. It will get pushed, and literally it's off the track, slightly off the track. What is the advantage of this kind of transportation? Rock and roller coaster, you go from 0 to 60 in like 3 seconds. You know, you take off really, really fast. Japan has many of these as their bullet trains. You go from like Tokyo to Osaka, whatever, in like 200 miles in what, 30, 40 minutes. Incredibly fast transportation. They're talking about putting one of those across the United States. I don't know. We'll see what happens. All right. The last are magnetic resonant imaging, MRIs. You guys heard of an MRI? What is the purpose of an MRI? Maria, what's the purpose of an MRI? Well, if it is cancer, I can also detect about an embolism in my, okay. The disadvantage of X-rays. Can you see tissue in an X-ray? Why? Because X-rays only bounce off of metal, and inside of that's calcium. So your tissues don't have any metal. So if I want to do an X-ray to see something, I have to inject you with some kind of radioactive dye. Is that always very good for you? No. Okay, but what they do in an MR, the magnetic resonance allows us to see a 3D image of tissue. My father-in-law is 78 now, and he's getting a little bit cognitive, he has some difficulties. So we took him to neurologists, and the neurologists were able to see every aspect of his brain, see where his nasal cavity is, be able to see all the in slices and in whole, be able to look at it in order to identify it. It gives us a huge image in that way. There's only one couple major problems with an MRI. Anybody ever had an MRI here? Okay, you did? Where? Where'd you go and have it done? Nico or this way?
I remember.
Okay. Did you, Alex? No, I couldn't remember, but I couldn't hear. What's that? They're what? They're pops? Your ears pop?
He heard it gets hot.
Oh, it gets hot. I can't hear the mask. I'm sorry. It doesn't get too hot. My son, Seth, because of his seizures, they had to take a look at his brain. The first time they put him in there, he was about a week old. Can you tell a week old baby to stay still? Yeah, so he had to be knocked out. When he was about 7, 8, we went to Children's, and Children's has a really nice setup. As you drive into the MRI, they have like different space images and little funky, kind of cool looking aliens on the side. And you go in there and they make it like a spaceship. It's this big round thing you go into. Now, in order to generate the magnetic waves, they produce sound waves. And so you hear pop, 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 and it's very, 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 very loud. Okay. Second's magnetic. So let's say you have, I had a guy I ministered in jail, okay, who had to have an MRI. He couldn't get the MRI. Does anyone know why he couldn't get the MRI? He had something put on his skin. He had a tattoo, okay? Now, unfortunately for him, he had a prison tattoo. Does anyone know what a prison tattoo is? They did it themselves, okay? With little pieces of lead ink, okay? Is lead a metal? Yes. So does metal get attracted at some level to magnetic forces? If they had put him in there with any metal in it, what would happen to that tattoo? It'd be literally ripped off his skin. That's why when you go in, they ask you, do you have any dental work that has any metal in there? Do you have any metal implants? Because the magnetic field inside will be strong enough to pull it out, or at least cause you a great deal of pain. Does that make sense? Now, incredibly useful for medical diagnostics, but there are things you need to be aware of if you're going to be a doctor, to ask your patients before you go sticking them in there.
What do they do if you have metal?
They'd have to go old school. They'd have to use an injected dye or something like that, because you can't, or they have to remove it, one or the other. Any questions? With that, we are done.